Our first speaker today is Christoph from Erlangen, and he's going to talk on uniform distribution in model sets. Christoph, you have the mic.
Yeah, thank you very much. I hope you can all hear me. I thank the organizers for this exceptional opportunity to speak here and present a talk in honor of Bob Mudis' achievements. I will go to my slides via screen sharing. So here we are. The title is On Uniform Distribution in Model Sets. Joint work with Gerhard Keller from Erlangen and Nicola Strungaru from Edmonton. As the title says, this talk is about uniform distribution in model sets, but not generally, more about a paper which Bob Moody published in 2002. It's a very short paper, as you see here, only 7 pages, but I think it's very influential, and I would like to take the opportunity in this talk here to talk about uniform distributions in model sets with emphasis on Bob's approach. This appeared at some time which was, I would say, very lively because many new ideas came into the subject. Mathematical diffraction theory was at its infancy. Maybe it started in 1995 approximately. And this was a very nice and very lively time. So maybe this is indicated with the remarks here, which appear on the first slide, on the first page of the manuscript. So what I would like to do is I would like to give you a geometric introduction into model sets, and in what I will be saying here, I would like to actually appeal to your geometric intuition. So what we have is a lattice in some, let's say, superspace. People sometimes say superspace. And the idea will be to produce an aperiodic point set by projection to G. So superspace is G times H, and we have a lattice living in G times H, and this lattice might be shifted by some vector X. And the idea of this cut and project method is to construct an aperiodic point set. And the first step is the cut step. So what you are doing is you fix a strip, and this you can parameterize by choosing a window, a subset of H, and then you just take all points inside this strip, and this is the cut step of the cut and project construction. And when we are describing this mathematically, we will use point measures associated to this point sets. And these measures we will denote by nu. They of course have an index, the window W, and they have also this torus coordinate. And what I indicated in green here is a fundamental domain of the torus. So this is the cut step. And the second step is then the projection step. And the projection step means projecting everything down to G. And this then leads to a measure which lives on G, which is just the projection of the original measure to the G space. And as you see here in this construction, this projection step is seems to be a bit more complicated than actually the cut step, because the lattice and the window, they might drastically interfere in a nasty way with the projection. Good. So just for setting and notation, the setting which we will be considering is the usual one where we say G and H are locally compact groups. They are assumed to be second countable to be a bit in an easy situation, let's say. And the lattice in general, it's a discrete co-compact subgroup of superspace. And the assumptions here, which are of course important, is that L projects densely to H and also injectively to G. And the window might be might have a very general form. It might be a relatively compact and measurable. And this setting is called, actually in this uniform distribution paper, a weak model sets. So what we will be describing here is properties of weak model sets, and we would like to describe model sets using measures, point measures, which correspond to the actual sets. So for the notation again, I've indicated this on the last slide, but we have torus points, which we denote by x tilde. X is just a vector from superspace. And we have this cut configurations called new w of x tilde. And we have this projected configurations, which we call new w with index g of x bar. And these objects, of course, live in some spaces. So the cut configurations live in the space of uniformly discrete measures, or g times h. And the projected configurations live in the uniformly discrete measures on G. Good. So we have a geometric intuition in order to think about model sets. But we are also, of course, interested in more, let's say, abstract situations where this might be applying to. And a puzzling example at the time was square-free integers. Call this S, the square-free integers. I will briefly explain this. They appeared in a number of theoretical considerations already in 1974 by Mirsky. Yves Meyer was also realizing that these are actually model sets. This was 73. Barker, Moody, Pleasance thought very much about these square-free integers and generalized variants in 1999. In particular, they proved pure point diffraction by direct calculation. And this was also later quite important in Zarnak's program on the Möbius disjointness conjecture, because these square-free integers, they appear as the square of the Möbius function. And this has actually led to a quite systematic investigation on variants of square-free integers by Lemanchik and co-authors, I would say. So what's a square-free integer? A square-free integer is an integer which is square-free, has no square. And this, of course, you can read off by the prime number decomposition by just looking whether you have a square or you don't have a square on the prime number decomposition. So in order to put this mathematically, you could just look at the corresponding group H, where you collect all of the residue classes for each P. It's an infinite compact group consisting of finite components. And the idea then is, of course, an integer square-free if this reduction modulo p squared is always different from 0. And this lets you define a subset of this group, which is a window, or which you could call window here, by removing the 0 from each component. And then, of course, an interesting, the natural construction is take an integer n and look at its reduction modulo p squared and call this n star. And then it turns out that if you define a lattice, then you can define a lattice by just taking this n and stars for all n and z, and you actually end up with a cut and protect scheme. So this is something where you might not have geometric intuition, but the nice thing is that you can use maybe geometric intuition in order to think about this number of theoretical problems. And this is a very nice idea. And this was maybe also this example was a motivating example in order to develop the theory of model sets further from physical applications, maybe in the beginning. So by construction, this set of square-free integers appears as this configuration in G now if the lattice is centered at 0, and it's a weak model set with compact window. But it's somehow nasty because the window has no interior points, and this means that the square-free integers have arbitrary large gaps, and even more, these arbitrary large gaps, they repeat in a very let's say, regular way. And what's also interesting is, if you now look at all model sets, weak model sets, which arise from this construction, then you can actually realize any subset of S by this construction. And this is also maybe astonishing, because you would think this underlying lattice structure would result in something which is very close to a lattice, but it's of course somehow different here, and you have pattern entropy and positive point density, and both actually are equal to the measure of the window, which you can express by a zeta function H2. Okay, so this is one example which motivated certainly much of the theory here. So let's think about point counting in weak model sets in a geometric way. Of course, the idea would be that if you would like to count the number of points in a strip, this should be measured by the volume of the strip. That's a naive geometric idea. And this should be true because of the cut and protect setup. Somehow you have some sort of irrational slope. G is an irrational slope with respect to the lattice. And the mathematical formulation here is the lattice projects densely to H. This is the reason here. But now the problem is, of course, that the projected lattice might not even intersect the window, and then you don't get any point configuration. So this will not work, this intuition, certainly if the window is bad. But if the window is nice, for example, compact and regular, almost vanishing boundary, then things shall be nice. And in this spirit, there are some density formulae around for certain weak model sets by different methods. And first method is analytic Poisson summation formula, dates back to Meyer even in the 70s. Second approach, maybe almost periodicity, Solomiak by Tilings, also Barker-Moody, the Greller paper. Geometric approach by Schlottmann by aligning a fundamental domain of the lattice very close, arbitrarily close to the strip, and then you can do fundamental domain counting. And dynamical systems approach dates back to Hof, Robinson, Schlottmann. I just gave you early references here. Of course, many people have worked about this later on. What we will be doing here, we will discuss Mudis dynamical systems approach. So that's the next slide here. First thing about dynamical system approaches to model sets. The big notion here is, of course, the hull of a point set. This dates back to Radian-Wolf 91 for Tilings. And the idea is you would like to study geometric properties such as asymptotic pattern frequencies. And of course, you know that these asymptotic pattern frequencies shall be shared also by translated point sets and point sets which are close to translated point sets, suitable topology, let's say local matching. And the underlying dynamical system then is called the hull of the point set. And the idea then here is to study properties of the hull and in a dynamical way, and then try to transfer those back to the original point set and hope that they are tell you something about the initial point set. And this way you can exploit tools from ergodic theory. So what Moody was actually doing or suggesting is not using the extended and the hull of the point set, but something which we would like to call extended hull of the point set. So the point behind here is, the idea behind is also, if you look at this geometrically, that the natural dynamical system is the torus with the induced G translation actions, such that if you take a point there and apply G, the point winds densely around the torus. And if you think about this, then for the point sets, this amounts to considering translations of the given point sets as before in the hull, but also shifts of the window simultaneously. So this is a bigger object, and Moody suggested it's interesting to look at this extended hull to derive something about the points that you are interested in. Here is Moody's uniform distribution theorem, 2002. You fix an averaging sequence which is called tempered van Hove sequence. I will not go here in technical details. I just leave it as it is. You would like to apply Birkhoff's ergodic theorem, Lindenstrauss version, and these are suitable averaging sequences here. If you think in RD, you just could take cubes. And then the statement is that the point density model set takes its expected value. It's the formula given here. And this is, of course, not in general for all point sets in this extended hull, but for almost all point sets in this extended hull with respect to the Haar measure. So this is nice. What you could then do, what was Bob then was doing, is applying this result actually countably many times in order to prove pure point diffraction for also almost all configurations in this extended hull, which is maybe an interesting and maybe also maybe unexpected result. And the point here is if the window is nice, a regular window, then the result actually holds for all configurations. But now, of course, the question arises, what can be said beyond this case also for square-free integers? Yeah, note that for square-free integers, it was already known that they are pure point diffractive by explicit calculations. But how does this fit in here into this dynamical description? This was unclear at the time. So before I go on and explain you a bit more about the setting, I will try to briefly indicate the proof of the theorem, which is a nice proof. So what you are doing is somehow you have to make the connection to pattern accounting, point counting, and geometry. And this is done via evaluating your measure at a test function C. Yeah, so C is some function completely supported continuous on G. You think of it being normalized and peaked at 0. And this function, of course, you can use in order to detect a point of your measure, or your point set at 0. So this is the first step. Now, what happens if you translate your point set? Or you translate your measure, then this test function phi c will detect a point at minus G. And this means if you would like to do if you would like to count points, then you just could write down an integral in the form given here, and the point frequencies are given by this integral, which is close to, of course, what you see in ergodic theorems if you would like to apply Birkhoff's ergodic theorem. Okay, so now the point is, instead of shifting the measure, you could also say, I apply the shift to the torus coordinate. That's the same thing. And this then means that you somehow can transport the problem to the torus, and you can actually use the torus dynamical system and the Birkhoff ergodic theorem there in order to evaluate this limit almost surely. And this is what is then given here in this integral. Now it remains to compute this integral. And what you have to study is the function appearing here. And if you think a bit about it, because it's sum, yeah, it's just an periodization, an L periodization of a very simple function on G times H. And the very simple function is just the product of C and characteristic function of the window. And once you see this, then the integral actually unwinds the quotient formula and or disintegration formula, and you just get the result. So that's a very nice proof. Okay, so now I would like to go on and say a bit about the torus parameterization, extended hull, and the measures, and rephrase these statements a bit into, let's say, more recent formulation, which Gerhard Keller and I, and also Nico Strongaro, have been working on. So the first point is to really view these concept of taking and translation vector, and then looking at the configuration as a map. So nu W can be viewed, should be viewed as a map from the torus into the point measures on G times H. So that's the cut, the map for the cut configurations. And likewise, you have a map nu WG, which gives you the projected configurations on G. And now you look at the extended hulls and give them the vague topology, which formalizes this local matching idea. 2 point sets or 2 point sets are close if they coincide on the large ball around a given point. And then, of course, you have also on these dynamical systems natural measures, which are the lifts of the Haar measures. And we call them Mirsky measures because, because in this square-free numbers example, they first appeared, these types of measures, frequencies of point sets, and people who are working there in this field actually use this name, and we think it's a good name, so we call them Mirsky measures. And what we would like to do now is we would like to refine Mudis theorem in specifying a bit more systematically measure measure 1 subsets related to Mirsky measures. So this is the next slide. So of course, in dynamical systems, very important notion is genericity of a configuration. And we call a configuration Mirsky generic, so here on G, if the ergodic limit exists for all continuous test functions. This is standard. Next notion is we would like to look at a slightly less restrictive notion, Mirsky K generic. And this also corresponds to these test functions we have seen before. So we require for K genericity not all continuous functions on the dynamical system, but only these of product type, K-fold product type, where you have these evaluations which we had before. And the geometric interpretation, of course, is Mirsky K genericity is existence of all pattern frequencies which have at most K points. And Mirsky genericity then by usual Stone-Weierstrass argument can be seen equivalent to existence of all pattern frequencies. And this we not only do for the Mirsky measure on G, but you also do it likewise for Mirsky measure on G times H. So these are the notions we will be using. Just to say a bit about this, of course, if you think of genericity, you get full measure subsets. So think here of the set of all points on the torus such that the cut configuration is Mirsky generic. And this is a full measure set. This is a standard argument. Also here, Birkhoff's ergodic theorem has applied countermilli many times. So for K, so this is a very strong condition. Yeah? For K genericity, Mirsky genericity, these are supersets of the sets of all Mirsky generic functions by definition, of course. And these are all then full measure subsets. And it's these subsets which we will be using. And there's also a relation between genericity on G and genericity on G times H, because the projection is continuous. So if you have genericity on G times H, this will transfer to genericity on G automatically. Okay, so this is some sort of collection of full measure sets which we will be used in order to state our results. So here is the refinement of Mudis theorem, O2, we call it, or might call it Mudis uniform distribution theorem 22. So here, what we use here is not only the configurations we had before, but we allow here for not only for characteristic functions of windows, but maybe some more general weighted model sets where we put a nice function h on the internal component. And the statement now is that the existence of this point limit is actually equivalent to Mirsky-1 genericity. And likewise, if you think of Mirsky genericity on G times H, this then is equivalent to existence of all, let's say, pattern frequencies for these embellished, let's say, configurations where you attach to internal space also weight by a CCH function. So this is immediate from the construction if you digested the proof. So now the question, okay, so the interesting question is now what have we learned, right? So this is a characterization and so on. Can we do anything with it? Yeah, and the point was Bob Moody was then continuing and proving pure point diffraction, and this does not rely on one genericity. So you know, something more has to be done, and how is this done systematically? And there's a nice answer, and this nice answer is that Mirsky-1 genericity, only this existence of density, might imply actually this Mirsky genericity for all k. And this I would like to explain. This is also based, let's say, result which is some years old, and in order to get acquainted to this, you could look first at the density formula for weak model sets, which says that limiting frequencies of a model sets are always bounded below and above by the measure of the interior of the window and of the closure of the window. And this is also, it dates back to Meyer and has been proven in using some different techniques over the time. And of course, this also yields the uniform distribution theorem for nice windows, but this also tells you that these two extreme scenarios, maximal density and minimal density, might be interesting. And the statement then is that if W is almost compact, written here, this is more than, or less restrictive than being regular, of course, then the maximal density of a configuration along A actually implies Mirsky genericity on G times H. And the same holds for almost open windows and minimal density, same argument. One example is then square free integers. And so it's nice, yeah, you have understood this square free integers example, and this led to numerous similar examples, B free integers, many results about B free integers, visible lattice points in various geometries and so on. Okay, so a bit of history about this result. So maybe it starts in 2013. So together with Christian Huck, we tried to prove an entropy bound for relatively compact windows, not necessarily measurable. And of course, we know that this is being attained for square free integers. And this conjecture actually appeared in an unpublished note by Peter Pleasance, who sadly died before. And it was attributed to Moody. And in this manuscript, Peter suggested that this might be proved by approximation by regular model sets. And Peter was right, and we proved it, and our proof also used the density formula for regular model sets, of course, at some stage. So then our proof was presented in 2014 at an Oberwolfach mini workshop organized by Barke, Damanik, and Uwe Grimm. And Nico was then suggesting, right after the talk, essentially using approximation by regular model sets, which he thought it's an interesting technique to prove pure point diffraction for model sets of maximal density. And this turned out to be right. Actually, I think that these approximation techniques, they are important and fruitful because you somehow deal with strongly almost periodic measures, and this might have actually led also to reconsidering these types of almost periodicity, which now have these interesting results about characterization of pure point diffractivity via Big-Sikowicz almost periodicity. Anyway, in fact, so this above genericity approach result is not only possible to prove by approximation via regular model sets, but it can be proved without approximation techniques. And we came up together with Gerd Keller by an alternative proof. And this alternative proof is also another consequence of another version of Mudis uniform distribution result. And I just, for curiosity, I just tell you about this result, this main proposition which we are using here. So you assume, and this is essential that W is compact. And then you formulate everything, not on the torus, but you formulate it on the extended hull. And you assume that you have any invariant ergodic probability measure on the extended hull. And of course you ask, is there natural density associated with it? And of course there is a natural density associated with it. And this natural density, this is, as you might imagine, always less or equal to the density, the Haar measure of the window. And the point here is that you have equality if and only if the measure you take is the Mirsky measure. And this is a refinement in some way of this uniform distribution result. And this can be used to prove this maximal density theorem. Good. So next thing, what we will be doing is we would like to make, let's say, the intuition precise that the extended hull should be actually isomorphic to the torus. Okay, so we start with the cut configurations and the extended hull from the cut construction, because this is somehow easy to see. And the statement here is if the window has positive measure, then the extended hull together with the Mirsky measure, and now this cut hull in G times H in superspace, this measure theoretically isomorphic to the torus. And the reason is now quite simple to see, because you use this torus parameterization map, UW. This provides a measure theoretic factor map. So it's first direction, and now you have to go back, but going back is also not difficult, because if you have a configuration and it lives in G times H, you can just look at the coordinate of the point. This is immediately given. If you just have one point, you can reconstruct the torus coordinate. And this is also a measure theoretic even continuous factor map, and having the zero coordinate in principle poses no problems, because this is only a zero measure set by assumption on the density of the model set, or on the positive Haar measure of the window. And these are mutually inverse, these two maps, and this is it. Yeah. So historically seen, the torus parameterization map was defined in the other way around. So in the spirit of this map attaching the torus coordinate to some configuration. But here we think it's a natural way to view this torus parameterization in this way. And yeah, we promote this site here. And now the point is, you would like, of course, to transfer now this result to the projected extended hull on G. And the first answer is this is a continuous map, so it's a factor of the torus, the extended hull, by the previous result. And this, of course, immediately gives you pure point diffractivity, and this is nice. But we would like to have, or we believe that we should have isomorphisms here. So how does this work? So this next statement here. So we need somehow a useful notion of a window, a period here. And what we need is actually a measure theoretic window period. So H is called H period. So it's a measure theoretic period of the window if W and W plus H, if you take the difference, a symmetric difference, then this is measure zero. This is some sort of generalization of topological periods, which people have used quite a bit. And now the theorem is if W is H is H aperiodic, then you have isomorphism of the projected extended hull to the torus. So in order to prove this, we use, again, Mudis uniform distribution theorem. But now we use the characterization of Mirsky genericity on G times H, actually. So what's the way we go? So we have to study the projection, of course, and the above result transfers if the projection is one-to-one on a large set. You can't expect that the projection is one-to-one on all of MW, but you would like to expect, or you would like to hope that you can do this on a set of full Mirsky measure, and then you are done. Okay, so now you have to analyze when this projection is one-to-one. And so what turns out is if you have two configurations in superspace and they have the same projection, this means that they have to coincide up to a shift in H. Okay, and now if you somehow can conclude that the shift has to be zero, you are done. And this is actually what happens if you take Mirsky 1 generic configurations. Then H is a H period, and in this case, if you assume aperiodicity, you are done. So why does this work? Somehow you have to transfer the information you have here about these configurations, that there are shifts in H, to this statement, it's a H period. And this you actually can do using this second part of Mudis 2002 theorem, because you have this freedom in order to attach here this compact continuous compactly supported function. And this gives you V convergence of these objects to the corresponding measures here. And this is enough to transfer this result, or this coincidence up to a shift, to this statement about H period. This is it. Okay, so now what do you do if you are away from H aperiodicity? And of course, you should also expect some isomorphism to some related torus, and this torus is a factor group of the original torus where you essentially factored out the H periods. And this is written here. In H, you can look at the H period group, and you embed them trivially into G times H, and then you get the statement here. So how do you prove this? It's a bit nasty to prove this because you have this measurable notion of periodicity, and the naive idea would be is do some sort of factor group construction and do everything. And what we did here is we constructed a measurable version of the window such that it has the same H measure, and it's actually fully invariant under let's say addition by a H period. And then we are in some sense in a topological framework, and we can do the usual constructions. Good. So far so good. Now we have quite a complete overview about these dynamical systems, and it's quite a general result to have this isomorphism to the reduced torus. Now let's come to diffraction. So we have seen in Daniel's talk also on Monday a bit about it, and I can briefly go through the same ideas here. So diffraction experiments start with a finite sample, lambda, and you are interested in the intensity of diffracted waves at a very large distance. Lambda is somehow close to 0. And what you are doing is you have an incident beam, X-ray, which physicists call monochromatic plane wave. And it hits the atoms of lambda, and the atoms will then emit waves which interfere in the whole space. And you're interested in the intensity at a certain position. And you assume that you have elastic scattering, so no energy is lost when doing this diffraction. The vectors have the same length. So what people then do is they define the so-called structure factor. So you have your finite points at lambda, points inside, and you have scatterer strength of the atoms called an FP, and you then attach the scattered wave, plane wave, to this each of the atoms, and this is called structure factor. And the intensity is essentially then given by the absolute squared of this function, but in a bit, let's say, complicated way, which you can extract from physics textbooks. It's given here. And this amounts to, if you think about this mathematically and would like to infer anything, just studying this process of going from, let's say, a measure to its Fourier transform, and then take the absolute squared finite point sets. So the structure factor, appropriately normalized, is called Fourier Bar Coefficient. And of course, if you're analyzing this, we think of an infinite idealization of the finite sample. So we start now with a point configuration on G, and we try to build this limit where we insert plane waves and integrate over it. And in general, this is done by characters, as this definition here shows. So this is called Fourier Bar Coefficient. Here's the result: existence of Fourier Bar coefficients for weak model sets. So the point is they exist if and only if the configuration is Mirsky-1 generic along -a. And this is the configuration actually in G times H. So this is the condition which gives you existence of these Fourier Bar coefficients, and you can also evaluate it to the form which is usually, which is known for some time, and this is the characterization. So here the point is typically, or very often, there will be a 0 for many values of chi, and the possible values of chi where it might be non-zero, you can explicitly give by, again, information which is due to the underlying lattice. So L naught is the annihilator of the lattice, and here we do not take all of these elements, but only these whose H component is invariant under this half period group. And this group is actually isomorphic to the dual of the reduced torus by Pontryagin duality. So somehow this gives the answer to the problem. And again here, this result relies on Mudis uniform distribution theorem, this refined version, which we cooked up. And so we need one genericity with respect to the Mirsky measure on G times H here. Okay, so this is the first result. So second result We go on to mathematical diffraction and going from the Fourier Bar coefficients, these individual objects, to objects which collects all of the information in one object. So we would like to describe this process of squaring the Fourier Bar coefficient for all characters simultaneously. And of course, as we know, this can be made rigorous, this approach, by using positive definite measure in their Fourier analysis. Essentially, this is Bochner's theorem. And this dates back to Hof in 1995, where he has been doing it in Euclidean space, temporal distributions. And I also think this, we will have discussed it very much in the 95 program on mathematics on long-range aperiodic order at the Fields Institute. So some sort of history here, which is unfamiliar to me because I entered the subject just after this time. Okay, so what you can do is you can describe this process. Daniel called this meaning of the autocorrelation in the following way. So you can consider a point measure, finite point measure associated with finite pointness point set lambda. And then you do the Fourier transform as before. This gives you a function then. In this function, you can take the absolute value squared here. But using a convolution theorem, you could also say, I could first look at the convolution of these measures and then do the Fourier transform as commutes. And then, of course, the idea is to infer the diffraction of this finite sample from that of the infinite idealization. And this is only well defined, as Daniel told, if you normalize appropriately. So what you define is the autocorrelation. In this way, this Eberlein convolution. And then everything is nice. Gamma autocorrelation is positive definite. It's Fourier transformable. Nicely, you have continuity of the Fourier transform on the positive definite measures. And then yeah, everything commutes nicely. And you get this statement that you can describe the experimentally observed diffraction asymptotically via its infinite idealization. And then you can talk about pure point diffraction and so on. Good, so here's the result, almost sure pure point diffraction, also here characterization, which is essentially, of course, Mudis work, but we have sort of specialized the sets of full measure where this appears. So the autocorrelation of an individual configuration exists if and only if this configuration is too generic along minus A. That's generic in too generic in G. And then you get the expected form here, and the autocorrelation is some weighted Dirac-Com, and the weight is then the covariogram, window covariogram convolution of the window with a reflected version. And the Fourier transform, of course, can then be done. It's yeah, and has the usual expected form. So note here again, we do not assume one genericity of the Mirsky measure here. This is equivalent to two genericity. So this means that in principle, we cannot expect this consistent phase property to hold. Those are two different let's say, assumptions we have here, but of course, you know, assume as we have this Mirsky genericity, everything works out nicely. So now let's, coming to an end, let's briefly make this connection to dynamical diffraction on the extended hull. So the dynamical diffraction, you can also yeah, describe by saying I have a natural autocorrelation here, which we can define by looking at all, let's say, all evaluations of Mirsky measure on two test functions, products of two test functions. And this means that the autocorrelation, as we know, encapsulates all 2-point pattern frequencies. This is one possible definition here. And now we get the result that the individual autocorrelation coincides with the dynamical autocorrelation if and only if we have Mirsky-2 genericity on G of the configuration. So this is one thing. The other thing is, this relates to the extended hull, but very often people say we would like to use the ordinary hull. So what's happening here? So if you assume that a given configuration on G is even Mirsky generic, so all K along minus A, and you consider the ordinary hull, which is just taking configuration and take all shifts in G, and then close with this local matching metric, then it turns out that this individual hull has full Mirsky measure, and this means that the systems are isomorphic. So this gives the relation, let's say, to the usual approach if you do not take the extended hull, but the ordinary hull here. Good. So next point is now having this nice, let's say, theory behind, which has been developed with respect to genericity for point sets which have extremal density. Can we say anything beyond, right? There should be examples. And we pose here one example, explicit example. You take cube-free integers and you take out the square-free integers from them. Okay, so what you can do is you can describe the cube-free integers, of course, as some cut and project scheme as above, as I showed you above, but simultaneously you can also in the same cut and project scheme write down a window for the square-free integers. So you have described them in the same cut and project scheme. Now you look at the difference window. So W prime is W minus V, and then it turns out the property is that the window W prime for this difference has empty interior. It's not so surprising, and that the closure is actually the window of cube-free integers. And this means that this model set fails to have extremal density. On the other hand, you can show that this window inherits aperiodicity, high aperiodicity from W or from V. And you can also show, this may be a bit more complicated, that W prime inherits actually Mirsky genericity from W and V. And this means all of the above statements, they apply to this set. And this is one example, maybe the first example, I don't know, beyond extremal density. And of course, you can cook up this example and make this a bit more systematic in order to produce other interesting, let's say, non-canonical model sets beyond extremal density. Good. Aftermath. And this is the last page of Bob's manuscript. And this is a very interesting page if you read it, not only for the references, not only for the remarks, not only for the acknowledgement, maybe also because of the citation here, which is appearing here. And I tried to think mathematically about this citation and try to interpret this mathematically. And when I did it, came up with the following conclusion. So the wind continues to blow. Yeah. So what have been done? So we have been analyzing genericity of a configuration. And this is a difficult problem, but it's an interesting problem. But it's so difficult that you can really think of, I lost everything, and it can't be said very much. Anyway, so what we have seen is that this approach to uniform distribution somehow shaped the analysis of model sets via dynamical methods. And of course, there are people working on non-abelian model sets and also almost lattices. Names are Björklund, Hartling, Pogorzelski, where all of these, let's say, structural insight might also be applied. And of course, we have a big interaction with dynamical system and number theory in these examples of set of multiples and B-free systems like people working on this, Lemanczyk Weiss and other people. Okay, so of course, this is some sort of list. The wind continues to blow. This is far from being complete. And any participant actually might make his or her own addition to this list. Thank you, Bob.